with the Codebook by Xanadu. This is something that was released last week, I think, and it's funny because there's been a couple of announcements around educational stuff last week. One was the Q Control Black Opal, which is a paid one though, and now you can get it for like $50 instead of like 180. You get like a 1 year subscription, I think, and a couple of months extra, like four or something. And this one is a free thing by Xanadu. And then what I wanted to do is just kind of play with this a little bit. And maybe instead of just starting from scratch, because this is like, I find this quite interesting, the navigation here. So instead of uh, just kind of starting from the beginning, I'll just kind of go through the simulation part just because it interests, I'm interested to see what do they explain there. Um, I think this is basically, okay, so what's the code book? So doing algebra. So okay, so the basics you need for the code book, I guess. And it's cool because there's some exercises. Exercise coder size exercise. All optional, but we encourage you nevertheless to work through them. All pen and paper exercises come with solutions. Click there below to see the solution. Okay, so this is the solution. Um, yeah, can't you see it? It's just codebook. It's just codebook at dot Xanadu. Yeah, just let me just put it in the chat. It's just these. Thanks. So and then there's come like some interactive things here with like add numbers, and I guess you just do like what like this. Is it like this and then just submit? Yeah. Okay. Cool. So um, that's nice. But okay, let's see. So this is just, and then there's like, whoa, a lot of modules here. So this is, okay, so this is more like introductory stuff about qubits. And it goes all the way down to like, okay, quantum interpretation. So there's actually some algorithms and some basics being done here, I guess. Control sets and control gates. I mean, it would be still interesting to take a look at these more in detail in terms of what do they explain, and I'll definitely do that. But I just want to kind of maybe skip that and go to the age. I just found it interesting that they go and they include Hamiltonian simulation. I just want to know what is it like? What does this chapter include? This is basic quantum algorithms. I guess this goes through the Magic 8 Ball. Okay, I've never heard this one before. Pair programming. Pair programming. Interesting. I mean, oh, but this is like I think just Deutsch or something like that, right? Is it? Making and breaking promises. So these are not specific. How do I transform? Okay, that could be interesting as well. From a content perspective and Deutsch users. Okay, so actually, that's interesting because it seems like they spend all these chapters just to introduce the Deutsch user algorithm, which is, I think this can be an interesting thing to take a look at. And then G, this is probably what, Grover. Oh, okay. And I think they'll just probably go and do the, yeah, and it's interesting. I wish I had time to, okay, so they go through the geometric interpretation. I mean, that's pretty much standard stuff, I guess. It's just, I guess everyone explains it in a similar way, but it's pretty nicely done. Like I just have historically, I have an issue with these type of explanations, which is that I mean, this one in particular is not, it's actually nice, but it's like, I believe there's a much better way, or I believe that it will be interesting and much, it's much more eye-opening if you try to explain things from sort of the first principles of interference and superposition and entanglement and stuff like that. And I think that Grover specifically has a nice game of interference that you can kind of explain. And if you just take a look at what the actual diffusion operator does, which is, to computational basis elements, if you take the computational basis element, say 1, what it does is it creates a superposition where uh, where basically that one element has the opposite relative phase to all the other ones, and it's not an equal superposition. It's a 50-50, so it's a 50% spread across all the other elements, and then a 50% stays for the elements. So it's a very specific superposition you're creating, which kind of makes sense then, because when you think about of these being run on superposition, you kind of have that concept of a superposition of superpositions, and then you kind of see things canceling out. Like it's a bit more like from my perspective, it feels a bit more like from a programming standpoint perspective. I don't know. It feels a bit more intuitive than all these, but there's no one explaining it like that, and I'm halfway through writing something like this myself, but we'll see. But that's cool. So let's take a look at, and I'm guessing they're going to add more things. Let's take a look at these 7 modules. We'll probably just do a couple because, as usual, there's not as much time as I'd like to have. But let's take a look at what. The thing is, I'm not so sure whether I should just focus on these first and then these, or you know what I mean. Like I don't know, maybe. Like this is a coding exercise, it seems to me, right? It says fundamentally quantum computing is different from classical computing because of the physical laws working under the hood. To understand quantum computing in this slide, it's useful to treat nature as a sort of a black box. It takes an initial condition as an input, evolves it using physical laws, and then you have an output. And so these are the measurements. We can try to infer the laws of nature by looking at patterns. So you have initial conditions, the laws of physics, observation. Let's start with a simple deterministic warm-up example. So in the code box below, you can print the results of applying the box to an arbitrary input, secret box, using secret box bits. Secret box? What do I have to do? Do I have to just run these? So I have to modify these. If I submit this, what happens? Incorrect. Oh, okay, but I see the output. And so it says the result of applying the secret box to 110 is 101. Okay, so I guess I have to figure out what the pattern is. Input. So I guess the input is these, right? So bit is an array. So if I do these, it leaves it unchanged. Let's see if I do these. Might be counting 1, 2. If I do 3, does it say 4 or something? No. So, oh, wait a second. Maybe this is just moving the things around, like shifting this from position to position. And I guess it just kind of, if I put it here, then I expect then the 1 will appear at the end. Yeah, at the end. So it's kind of taking the elements. Oh, let me see. Maybe just it actually works with non-numbers. Like, what if I just put a string? A, B, and 0. I can just mix it up, I guess. Yeah, there you go. Okay, so this is these, and then things kind of just slide. I think there's a way to do that in Python instead of just like doing a for loop and whatnot. Can I just shift list elements in Python? I think there's just there's a native function for these. Rotate to the right. But I want to rotate to the left. Python left rotate array. I'm sure there's a function for these. Rotate. Left. I mean, so I thought there would be something like shift list elements to the right and shift list elements. But if not, I'll just do this by hand. But I guess I thought there was a I thought there was a like a function. Oh, DQ. What if you're trying to shift the elements? Use DQ rotate. Okay, but I have to import that. Why though? What does rotate do? Python rotate. I'm spending already too much time with this. um, uh, anyway, I think it's easier just if I do something like so I have like a temp that is basically, you know, that is basically a an array of how to do this in Python. I'm a noob. I think I can just oh, I can just do this. Okay, it's a bit it's a bit dirty, but so the range will just be basically the length of beats, right? And so basically what I will do is so for the in beats, basically what I will just do is now is this going to give me the index or is this going to give me the, I never know that, Python list index iterate. I think I can do something like with the index. I think I can just do something where I, yeah, enumerate exactly. Exactly. So I just have a bad memory for these things. It's enumerate, right? And the index and the element. Okay, cool. So basically what I do is, you know, just very, very simply put, if index is 0, then I'll just put temp of, you know, len bits minus 1 equals b, else if index is len bits minus 1, you know, kind of I'll just kind of hard code these, right? And say then temp 0 equals b, else basically temp index minus 1 equals b. So I just kind of like move things to the left, right? And then what I return is I returned temp. Does this make sense or what? Or it's too time consuming? Invalid syntax? Yeah, well, I have this nasty thing here. Maybe I gotta put parentheses here, I don't know. Line 22. What is the problem? What is the problem? If, else, if. Is it with the if, else, if? Ah, it's elif. No way. No way. No. Consent. Elif. It's elif. Oh, I think that's a problem for sure. Elif, statement S. If, elif. Yeah, cool. Okay, guessed it. Okay, cool. But then what does it say here? So can I just close? I can close that. I can close that. But can I go back to it or? Oh no. Okay, so you click show challenge and that's the challenge. Okay, so the challenge is just the, so you can hide that and focus on this. That's nice. Describe the distinction between, so learning outcomes, describe the distinction between behavior, deterministic, random, and quantum systems. Okay, so I think we can, okay, what does it say here? So what makes quantum computing fundamentally different? I don't know if you guys can read this. Probably should zoom in a little bit. I don't know how's that going to behave though with zoom. Probably better. Yeah. So what makes quantum computing fundamentally different from classical computing? It's the physics going on inside. To help understand this, it's useful to abstract from specific computational models and instead think about physical systems in general as black boxes where initial conditions go in and then wait for some time and then we observe. And in between, then the physics happens. And so that's what we, initial conditions, the laws, and the observation. Often even knowing the laws of physics does not allow us to predict what the black box will do. At least with pen and paper, the math is just too hard. An example is a three-body problem. Of three planets interact gravitationally, they perform a do-see-do so complex that there is no explicit mathematical formula for it. In this case, we can do something more radical than math. I guess you're going to simulate stuff, right? So that's cool. Imitates or simulates the black box of nature. We can call this human-made black boxes computers. So that's what nature would do, and then that's a computer simulation, which is just an approximation, but it serves, I guess, to understand what the systems a bit more in detail. Most physical laws are continuous in this sense; they act on systems that cannot be split into finite set of components. Like I mean that's a bit I'd say what you can't split is kind of maybe not the components of the system, but rather sort of the evolution of the system, right? Because it might be that you deal with discrete subsystems. In contrast, most computers, though not all, example, a slide or rule, are discrete, acting only on a finite number of components. So to turn continuous laws into discrete computations, we need to approximate the better we want our approximation to be, the more computing power we need. And so that's the limiting factor. Okay, so here's some broad classes of black boxes: classical deterministic systems, classical physics, natural laws, classical physics, from mechanics, electromagnetism to gravity, takes the form of a classical deterministic box. Oh, so there's an exercise. Let's see. Our model problem will involve coins, though really this is just a colorful way to talk through binary digits. So let's consider a system of n coins laying on a table. Each coin can be in one of two states, heads 0 or tails 1. We will describe the state of the system by a vector of n bits. So exercise, how many variables do we need to describe the state of n coin system before it passes through the box? How many different configurations does the system have? how many different rules are there for deterministically evolving the n-coin system into a new, that's B. So how many variables do we need to describe? In this case, I'd say, well, you have n coins, and so you need n variables, right? So, and that would be that would be my guess. Hopefully, it's not wrong. And how many different configurations the system can have? Well, that depends on whether the order matters or not. I guess, does it matter? Well, it can have if if this is just, I'd say it's as simple as if each variable can have two values, then it's 2 to the power of n, right? So this means you have two possibilities, but for each of these two possibilities, you have two more possibilities. So it's like 2 times 2 times 2 times 2, and then it's n. So that's at least for A. That'll be my guess. And B, how many different rules are there for deterministically evolving the n-coin system into a configuration of n coins? How many different rules? I guess it's just I guess it's just one rule. It depends on how you define the rules, right? So you could just say um, like it depends on how powerful the rules can be. Like you can think of the rules, if the rules just, if you just have a set of rules that say, I don't know, you can say look for a given coin, like coin number 3, kind of change the value, right? It's the only thing you just with like a change value instruction, that takes you from 0 to 1 or 1 to 0 should be enough. So my guess is that one rule is enough. And then, yeah, you could also say, well, if the specific coin you want to change is something, if you can't parameterize rules, then you need n rules, right? Like one per qubit. But I think that would be maybe a stupid way to think about this. Let's see, let's see, let's see. Okay. So I think I, what was that? So A, the classical value of the coin J is very low. Yeah, so 2 to the power of n, since they're n variables. So I got that. I got that. This was an easy one. And then for classical deterministic systems, there are 2 to the power of n possible inputs. Each of these may be associated with any other configuration. Okay, then I didn't understand the question. How many different rules are there for deterministically evolving? Like I understand rules as in like an updating like rule, right? So like you're given, so how many rules do you need? But it seems here they're talking about like how many transitions you can have, right? So if you have, yeah, which makes sense, then the answer, if you have 2 to the power of n possible inputs, and then each input can go to 2 to the power of n different other outputs, like itself or any other configuration, and so then you have 2 to the power of n exponentiated to the 2 to the power of n. That makes sense. Yeah. Cool. A second more general class is the random systems. Here an input sometimes results in one output, sometimes in another output, varying randomly. One randomness can arise from dynamics. So one way this randomness can arise is from dynamics which are in fact deterministic, but we ignore or don't have access to certain details of the system. So the most famous examples is statistical mechanics, which is that would be cool to take a look at some point. I've never done this. It's a mathematical underlying thermodynamics. I didn't know that. Really? Is it really so? Look, something new I've learned. Why? Hmm. I'll be interested to know why. Why is that you need to use statistical mechanics to model thermodynamics? But yeah. It turns out that it's not just possible, but useless and unnecessary to keep track of the precise deterministic evolution of each of the 10 to the power of 26 particles in a handful of dust. It is much better to talk about the statistical tendencies of this handful. Okay, that's why, probably. Um, so Suppose that we are now allowed to flip our n coins and introduce random outcomes. In particular, we'll assume that black boxes can be described by conditional probabilities. P, Y, X, probability of observing Y given input X. Okay, that's gonna get messy. I'm bad at probabilities. Um, let's explore how this differs from the system. So we have and then comes quantum. Um, so how many variables are needed to describe the current state of the system? Since probabilities are continuous, like I like the exercises sort of embedded in there because they really kind of even if they seem innocent and like easy, they kind of force you to think about this stuff. It's too easy nowadays to just read through tutorials and yeah, you can skip them here, right? But yeah. Uh, how many variables are needed to describe the current state of the system? Okay, let's try to think about this. Um, how many variables? I mean, it's still to describe a state is the same, right? You have n coins that can be 0 or 1. Ah, okay, probably not. Would you? So maybe yeah, okay, because now it's probabilistic. So it's a coin can be probably in state 0 with probability, p, but then the state 1 is 1 minus p, right? So actually p, I mean whatever probability. So it's still n. You don't need 2, it's still n, right? Because they must add up to 1. You could naively say you need a probability for the 0 state, a probability for the 1 state, but you don't have to. So that would be my guess. And then part B is, since probabilities are continuous, there are now an infinite number of black boxes. Show that, yeah, okay, black boxes in terms of all the different connections, right? Because you can say, well, I can have a probability of like a system state where it's all probability 1, for example, but then there's one coin that's like probability 0.02, another 0.003, like it's a real number, right? So show that 2 to the power of 2 to the power of n minus 2 to the power of n independent probabilities are required to specify a black box. Okay, let's think about these. Maybe I should actually get pen and paper, to be honest, but let's try to do this just like on the head, roughly. Okay, so we're talking about specifying a black box, right? So to specify a black box is like what happens. So probabilities. To specify a black box, this means to specify the whole of the actual laws of physics in this case, right? I guess, I mean, you have n coins. The n coins. You have 2 to the power of n, right? 2 to the power of n. It's like I can do a bit of, I think I can do a bit of breaking these down, right? Because this 2 here is probably because of the 0 and 1s, right? So this is probably just because it's a 0 and 1, and so and then 2n, it's probably got to do with the probabilities of 0s and 1s and stuff like that. I don't know where the minus is coming from though. So I'd say the um, I have I have a 2 to the power of n possible states. That's my input space, right? Now there's just an infinite number of now I know. Okay, so what is the most generic way to specify how things can change? Well, yeah, no, actually you're right. I don't have no, I don't have 2 to the power of n. That's wrong. I don't have 2 to the power of n possible states. Um, because then I just have different probabilities for each. So I have an infinite number of here I also have an infinite number of possible states, right? Uh, Independent probabilities are required to specify a black box. To specify a black box, I need to specify like how to take how to transform an input to an output, right? Um, in a way, the way that I'm thinking is like in a way you could think of I'm maybe thinking too much like from a programming mindset perspective, uh, with ifs and else, right? So you're like, okay, so take that probability and do something with it. But I don't really like what I'm missing here is I'm missing the what is it that is needed to transform? Because here in the previous example, right, it's like it's a pure mapping. So it's a pure mapping. You just map things. This evolves to that, like, and that's your deterministic system. But here, oh wait, no, wait. Let's back up a second. The output is an actual string, or is an actual set of like n coin results measurements. That's actually what I'm getting wrong. So actually, there is a the domain, or the possible outcomes are really just 2 to the power of n, right? You can think of these independently and say, I don't get it though. I don't get. I absolutely don't. The thing is, I don't know I don't know what are the requirements for such a black box. You know what I mean? Like that's what I'm missing. Um, and the classical system is just a mapping. You have this input, which then deterministically evolves to that other input. Now here if I have an input, right? It can, okay, if I have an input, it can actually take me, if I have an input, it can take me to, um, in the most generic case, to 2 to the power of n different outputs, right? Because this means it's like a measurement. So each qubit can then be measured, each qubit, sorry, each coin can be measured to be 0 or 1. And so I need this, I basically, but then they don't affect each other, right? So um, how would I specify the black box is, or that's the measurement part, 2 to the power of n possible outputs each input state. But then the laws of nature is like how things evolve for each. So a state has n coins, right? These n coins have each like two possible values with associated probabilities. So um, so I do have 2 to the power of n possible sort of skeletons of input states, and for each of these I have to basically the laws of physics have to tell me how each of these probabilities evolves, kind of. Does it? because that could be these, right? But then I don't know why minus, because there's some redundancy. I think I'll let's think about this again. So I have the problem the problem I'm having is that I don't have I'm not so sure what is it what does it take for the black box to be defined, right? The black box is just the laws of physics. So basically it's just telling you how inputs map to outputs, right? How inputs map to outputs. In this case, we have an input that is n coins, and each coin has you just need one probability to know what's the probability of measuring zero or measuring, like for example, right, measuring zero. So you know the one measuring one. This means that the laws of physics basically have to catalog for all the possible combinations of no, that's wrong, because it's just you don't have these coins, you just have the probability. So you have, for each coin, you just have a probability. So the laws of physics should tell you, first of all, it's like a two-step thing, right? So how things evolve in time. So how each of these probabilities evolves in time. So this means to me, this is like to me, this is like how each of these n probabilities evolves in time. And then still, I have to remember the randomness here is because we don't have access to the information. Does this change anything? Mm, does this change anything? So I have independent probabilities are required to specify a black box. I need to basically, to specify the black box, I need to tell, I just need to tell, to me, it's like, I just need to tell the system how to modify the state. So I just need I just need, I just need to specify how, oh, maybe I'm getting that wrong, right? So what's random is the evolution, not the states. If because I'm assuming all the time that the state is per se random, which is wrong. So it's like a state is a state. So state is still like a state is really look. No. I'm and the problem is that the problem is that I'm getting spot because of the quantum stuff, that it's in a way interfering with my thinking. But so the state is actually the 2 to the power of n states that you can have. Like in a way, you can define a bit of a classical superposition, right? So you say the state of my system is basically an ensemble, or like a mixture of like all the possible states that my system can be in. So my system can be in 2 to the power of n states, and then for each of these, I need an associated probability. That's kind of the definition of my state, because it basically tells me, okay, so maybe it's like 10% chances in this state, 20% chances in this state. In the most general case, I have total uncertainty, and so I just have 1 divided by 2 to the power of n, so all states. So this means I need 2 to the power of n. So I need 2 to the power of n probabilities to define a state. Can I check first if that's correct? Because that's going to help me with these. So I'm going to try to open the solution, cover it. Well, no, come on. My first, no, no. So my first, wait a second, but I'm not looking at it. Each coin has remained sufficient. The value xj. Wow. Huh? So a state is a state. Okay, so I thought, then I got this wrong, right? So okay, so the input sometimes results in one output, sometimes in another. So the evolution is random, because what basically the solution he is telling me is that for A, it's like it's still a deterministic state. It's still like a, okay, n coins, right? So yeah, you need n variables, and now let's try to play the. So I was wrong in both versions. So now let's try to get that right. Yeah, so basically for each coin can evolve with a probability p in one direction or in the other direction, right? Um, so actually you need two numbers, right? So no, do I? Oh God. It seems obvious, but it's not that obvious. So so if this is just the system, the state is the state, like the state is just a state. And so now I have a state, and this state can basically evolve. Okay, let's not think about specific subsystems, but but the state as a whole. So each state can evolve into 2 to the power of possible different states, right? Because I think that's what this is saying. It's like for each coin, so for each coin, right? That's where the validity 2 is coming from. Like for each coin, like I can either go the 0 way or the 1 way. In each case, then like and I can do that two times n. I think that's where this is coming from. Yeah. But it's confusing because in theory, you just need one probability. If your system is 0, 1, right, and you want to keep that, that's what's confusing me. I'd say you just need one probability, not two. But let's see. And then this is counting for some redundancy in what? I think I just probably should take a look at this. I'll never finish anything here. I have barely gone through the H1. But kind of my guess would my guess my guess is and try to reverse engineer that, but I guess like you need just one probability per coin because the other one kind of comes defined already by like 1 minus p. So you'd say uh, for each coin you can go one way or the other. So I would say 2 to the power of n, not like 2 to the power of 2n. Yeah, I don't know. That's definitely the way I would think about this. Not like this seems to indicate the other way around. But let's see how they justify that. So if it seems at first that each p y x is independent, um, oh, maybe that's because of the okay, that's because of the you define the probability of observing y given input x. Uh, so you have 2 to the power of n possible inputs. Yeah, okay. So it seems to us that each p is independent, which would give a total of 2 to the power of n squared parameters. But for a given x, Pyx must be probability distribution over y, and so Pyx must add up to 1. This gives us a set of 2 to the power of n constraints. Oh, it's not, but what? I'm confused. It seems at first as if each probability of observing y given x is independent, which would give a total of okay, so because I got to these differently, right? For me, it was like, so for each subsystem, you can go either 0 or 1. So you have you kind of have these two probabilities, and then you do that. N times. Oh no, yeah, that's wrong because it's thinking about the states, observing states given inputs, so not about thinking about the subsystems. Yeah, that's what I didn't pay attention to. I didn't pay attention to that. That's the way that the laws are defined. So you have a probability of observing y given input x. So you have 2 to the power of n possible um, observations. So it's pretty basic one, but I'm still not so sure why you can't approach it from the component perspective, but then from the subsystems perspective, like you'd say each coin has a probability to evolve, right? And here what they're saying is they're just saying that there's a probability of observing y given these as the input. Yeah. So you have the two, right? Because you have one for the x equals 0, one for the x equals 1, and then for each of them you have 2 to the power of n possibilities. That makes sense. But why don't you get, but then you have the constraints, right? Because these probabilities must add up to 1. But then why don't you get to the same result if you think about each of the components independently? If you say, I have a state and then with n coins, and so each coin can really go one way or the other. So you have a probability p. So you have like, yeah, okay, but you can't really just go that way because that doesn't tell you. Yeah, well, it does, no, right? Like you have p independent probabilities that tell you how each subcomponent would evolve. Um, and so with just p probabilities, you should be able to. I mean, that's interesting, right? So why wouldn't that work? I get, so this is defined over the sort of the whole state space. So maybe the way that I was thinking about it in terms of subsystems kind of just opens it up for more. I don't know. I have to come back to these. I definitely would love to come back to these. why can't you just define that instead of just at the state space level to just define it for the subcomponents and say I have n coins, and so my loss will just basically be defined as in like what is the probability of each coin evolving from one state to another, right? And it's or what's the probability of each coin changing, kind of. That will be so you have p possible probabilities you need to define, and that's it. P n, not p, n. Like, wouldn't that be better? Because that is that is like a way bigger number, right? If you want to define the loss of probability, the loss of that system like that. But I'm quite sure I'm overseeing something. Um, but anyway, I don't think I'm going to make it to the quantum stuff. But what is the quantum? So let me just different random observations. But these outcomes have some curious features that cannot be explained by classical randomness. Let's imagine that we have n coins and qubits are in the state. Important difference between similar in the state of classical systems. So how many classical deterministic variables are needed to describe the state of a system? Yeah, okay, but that's a bit like okay, because there is an assumption you've gone through all the qubit stuff before, right? So I'll try to see if I can do that later. Actually have to go, but um, yeah, that was definitely yeah. I definitely want to go. I definitely want to keep going through these. I think I'm gonna spend some streams in here. Chapter 2 is unitaries. Okay, cool. We'll see. That was interesting. I still don't know why you can't just do the maybe I'll ask this in Twitter. Why can't I just define the system, the black box, as in like just with n different probabilities, right? Of each of the subcomponents. They're independent from each other, aren't they? That's I think a fair assumption to make. Maybe not. Maybe that's why. Maybe that's why. Maybe that's why. Anyway, that's cool. I definitely recommend the codebook. It's interesting. At least just after I haven't even finished H1, but I'll definitely try to go through all these in the next streams. I think it's kind of a good exercise. Yep. Cool. Bye bye. See you next time. Hopefully soon. Really soon.